Hi, my name is Clive Andrews, 2E0DSD, and this is my presentation called Hunting Down QRM. It was presented to the Farnborough and District Radio Society on the 11th of March 2020. As a footnote, QRM is the Q code for human-generated interference, as opposed to QRN, which refers to atmospheric noise. Last year I did a presentation on SDR dongles and found some potential QRM issues in our bungalow. One of our club members would like to install a solar PV system and he was worried it would spoil his hobby. So he asked me on the forum if I could investigate what was going on. In this talk I will show some pictures of our solar PV panels in the inverter installation, give a brief history on EMC testing, look at CE marking, the test equipment used for measurement and the test limits, hunt down some QRM in the bedroom of our bungalow, describe some methods to suppress QRM, and come to some interesting conclusions. I have included web links to my source material at the end of the talk. The picture on the left shows 12 260 watt solar PV panels mounted on the roof of our bungalow, and these give around 3 kilowatts of peak power. The right hand picture shows a Solax XK SU3000 3 kilowatt inverter charger, and this is mounted on the wall above our bedroom. The two Pylon-Tech 2.4 kilowatt hour lithium batteries give a total of 4.8 kilowatt hours of usable energy, and these are mounted on the floor in the bottom right hand corner of the picture on the right. The requirements for EMC testing started at the turn of the century when lightning was found to interfere with the telegraph system. The German telegraph law was brought out in 1892, the London Lightning Act in 1899, and in 1906 the International Electrotechnical Commission, or IEC, standards were established. In the 1930s we get the American Federal Communications Commission, or FCC as we know it, and we also see the Verband der Elektronik, or VDE, established in Germany, plus various other organisations in Japan and Europe. In the 1970s we saw microprocessors and switch mode power supplies finding their way into offices and people's homes. The QRM from these early designs was causing interference on people's televisions, and they were complaining to the government. So the authorities started to look at stronger standards. Mandatory EMC testing started in the 1980s. Testing for the CE mark includes mechanical, electrical and safety tests. Mechanical and safety tests look at the integrity and flammability of materials, and electrical and insulation and potential shock hazards, etc. The EMC directive deals with conducted and radiated susceptibility tests and looks at how much electrical noise comes out of the mains plug, how much electrical noise is radiated by the device, and does the device fail if you expose it to RF. Conducted emissions cover the range from 10 kHz to 30 MHz, and radiated emissions cover the range from 30 MHz to 1 GHz. You should beware of the Chinese export mark. Some devices from a well-known auction site may not have been tested correctly. From the previous slide, we can see a division at 30 MHz for conducted tests and radiated tests. This split is based on some general observations that below 30 MHz, RF problems are usually related to noise conducted through the mains power line. This noise is then re-radiated by the house wiring. From 30 to 300 MHz, the emissions or RF immunity problems are generally associated with the external cables acting directly as antennas. Above 300 MHz, everything becomes a suspect. Cables, seams, openings in the enclosure, These can all act as hidden antenna. Even tracks on a PC board can act as RF radiators. If we keep the above information in mind, it will help us in trying to find and suppress any unwanted QRM. The first photo shows a spectrum analyzer with a line clamp around the mains lead of a multi-tool. The second photo is of a line impedance stabilization network, or LISN, that can be used to detect RF from the device under test or inject RF signals back into the mains plug for susceptibility testing. Here we can see an EMC test chamber, and these are typically the size of a small barn. The walls are lined with ferrite blocks and foamed metal cones to absorb RF reflections. Tests are typically performed with an antenna at 10 meters from the device under test, the DUT, and tests are repeated for vertical and horizontal polarization, and the device under test is rotated on a turntable to expose each face to the aerial. Some tests may be repeated with the antenna at different heights. This is all automated within the chamber, and you don't normally have anyone in the chamber with the equipment when they're running the tests. A common standard for CE marking when I was working on power supplies was IEC 62368 or EN 55022 for small office equipment. I'm a bit out of touch with current standards, so these have probably been superseded by something else. Standard documents typically cost upwards of £40 each, and you usually need a set of 3 or more to get all the information you need to prepare for a design for testing. Test limits are generally grouped into 4 classes, and the table shows industrial products are allowed higher emission levels than commercial products. The theory is that factories are away from domestic residences, and the factory walls will attenuate emissions by more than 10 dBs. Military and medical products have tougher limits than commercial products, and avionics and automotive products have the toughest emissions of any CE testing. The test limit graph shown here was taken from a Texas Instruments datasheet for a small switch mode power supply. Measurements are taken using a clamp-on coupler or a LISN. The maths for converting these limits into something meaningful could get complicated, so I found some handy conversion tables on the web. The worrying thing is that the measured signals equate to around S9 plus 10 dBs in ham radio speak. Hopefully the local wiring will not perform very well as an aerial. Radiated emissions are performed in an EMC chamber using a calibrated antenna. Once more, I will cheat and use tables from the web. Again, the limits calculate at something around S9 plus 10. As you can imagine, professional test facilities are quite expensive. From my experiments, I collected together my trusty SDR Play RSP Duo and my Texan PL880 portable radio. For antenna, I used an old magnetic loop antenna from a mini hi-fi system and my Bonito active aerial. As you can see from the picture on the right, I set up the active aerial on the bed under the PV system in the roof and hunted around the different bands to see what I could find. The most interesting band for the purposes of this talk was on long wave. By moving the active aerial around, I confirmed that the 6 peaks of noise were coming from the PV system. The fuzzy band of noise around 190 kHz was also from the PV system, but the band of noise centered on 240 kHz appeared to be coming from my PC. The level of the noise rose up and down as I moved my finger over the PC touchpad. By tuning the portable radio to around 290 kHz, I could get different levels of buzzing from the PC screen. Interesting, I did not get any buzzing from the portable radio if I tune to any of the PV unit peak frequencies. I took my portable radio into the loft and hunted around for buzzing noises from the PV system. I did not get much pickup from any of the wiring, but did get strong buzzing if I placed the radio near the centre of the white casework. I noticed earlier that the noise from the PV system varied significantly as I moved the active aerial around the room. If I placed the aerial near the bedroom door, I could get an acceptable signal for radio 4, and the PV noise spikes were significantly smaller. In fact, I found moving the aerial into the living room improved the signal even more, and the signal in the garden was very strong. Although the noise from the solar PV had gone, the PC still showed up on the waterfall display. From the specifications discussed earlier, we know the near-field emissions from household appliances can be of a similar level to the wanted signals indoors. So the simplest thing may be to just move the aerial around to get the best signal in the house. I found the magnetic loop performed slightly better than the active aerial system. So what if we wanted to try and suppress noise signals at LF and HF frequencies? We know that under 30 megahertz, RF emissions are probably conducted and re-radiated by the power lines. So inline filters are good for suppressing signals below 50 megahertz, but the PV has high voltages and is rated at 3 kilowatts, so we would need a big filter. The Topaz isolation transformer in the picture is from an old EMC lab and is only rated at 125 VA, and you can see how big that is. Screen cables are good for around 1 megahertz to 10 megahertz, but this would not be practical for house wiring. The inductance of an earth wire exceeds the resistance per unit length for frequencies above 10 kilohertz. The PV unit is a long way from ground, so earthing may not be very effective for RF shielding. VHF and UHF suppression may be a little easier than at HF. From 30 MHz to 300 MHz, any RF emissions are probably associated with external cables acting as hidden antenna. EMI clip-on ferrites are good for suppressing RFI from 50 to 500 MHz, and you can enhance their effectiveness at lower frequencies by winding a turn or more of cable through the ferrite ring. USB cables can emit RFI from 30 megs to 200 megs or more. You need good quality shielded cables with ferrite suppressors. Switch mode power supplies can emit RFI from around 200 to 400 MHz, so ferrites provide a good suppression solution. So what conclusions can we come to from all this? It can be confusing when you are looking at SDR signals. So a good strategy is to try different locations to home in on any interference and try different types of antenna to see what happens to the received signal. Handheld radios are good for hunting down QRM by sweeping them around the target area. We have seen that the CE radiated emission signal levels are similar to the DX signal levels that the amateur radio operator is looking for. It can be difficult to suppress RF noise at LF and HF frequencies, but VHF and UHF noise can be dealt with by using clamp-on ferrites. The best approach is to choose the most appropriate antenna for the band. A tuned antenna is particularly good at rejecting RF noise, and you should try to find the best location for the antenna, preferably well away from the house. This concludes my presentation, and I have listed some useful web links that I used to prepare this talk. Thank you for listening.